Alright guys, want to do a quick video here about polynomials, and what I've got is an example we can see here on Desmos. A couple of things to point out about this particular example. So over here on the left hand side of the Desmos screen we can see the factored form here in red and the standard form here in blue. Now I say standard form, usually we do want to rewrite that standard form. We can't see it right now, but what the biggest exponent is, so over here on the right hand side, usually we want that flipped around. We want it to look more like this right here, where that x to the sixth power we see is coming first, then it's going in descending order to the fifth power, to the fourth power, third, second, first, constant. And if anything is skipped, it's okay to leave that section blank in between. So if there was no fifth power part, that part could be deleted out. Now, what we want to see about these two particular things is that the factored form in red works just like factored form did on a quadratic. So here we're dealing with a sixth degree polynomial. What we're saying is that that factored form, so there's three factors, that's one, that's two, that's three. Basically one set of parentheses is one factor. And what we want to see here is that that gives us three distinct zeros, right? Those three coordinate points highlighted there on the picture are the zeros for this particular polynomial. Now, we are going to want to learn ways and strategies to deal with polynomials in their standard form to find their factors or to find the factored form. We're not going to be dealing with factoring polynomials of this magnitude. This would be too difficult of a procedure for us at this point. But with some insight into how factors work, we will be able to do what we call decompose this particular sixth degree polynomial down into the factored form, or just be able to find the other factors. So for example, we might be able to eliminate some of these potential zeros from the problem and then reduce this polynomial to be able to find these other two examples. So I'll show you that in a moment. But what we want to see here first is what we call multiplicity. So a quick concept understanding here is that multiplicity, so let's use a different color here, multiplicity is invisible when we're in standard form. We don't really see it here in this equation. Well, I say that. There are ways to see it, but we're not going to learn those ways. What we really see multiplicity by is the exponents in factored form. That's the easiest way to see what multiplicity is. And those exponents here are 1, 2, and 3, giving us a multiplicity at each of those zeros. So the first zero there, x plus 3, is occurring over here at negative 3. And the way that we see that is not only by the exponent, but by the shape of the graph at that particular zero. And what we want to see is at that particular intersection there, the x-axis, right, where this is crossing the x-axis, we get this very linear pattern. So a first degree multiplicity or multiplicity of 1 cuts through the x-axis like a line. And the way that we can see that, so it's really nice in Desmos because I can just zoom in. So what I'm going to do is I'm going to zoom in so that the rest of this graph is invisible, can't see it. And I've zoomed in so far that if you were just looking at this particular picture, that picture looks like a line. So that's what I mean by it cuts through the x-axis here. If I just zoom in on this one particular section, don't look at any of the other details, that's a very linear look. And that's what the first degree looks like, right? So the second root that we're going to look at is the root over here, which based on the factored form up here, that's this root, x minus 2 squared, has a multiplicity of 2. And when we have a multiplicity of 2, that's going to make that U shape and bounce off the x-axis. Okay, so when we say that and we zoom in again, ignoring all these other details, if I just zoom in far enough here at that particular point, what I want to see there is that U shape of this graph bouncing off of this x-axis. Okay, and that is what a multiplicity of 2 looks like visually. Factored form, it looks like this repeating x minus 2 factor. And we'll talk about that in a second. And then finally here, we're going to look at the last 0 on this image, which is this 0 over here coming from the factor that has a multiplicity of 3, an exponent of 3. And when we talk about that here, we're going to say that that sort of swerves through x-axis. So really here, this should say cuts through me and my terrible spelling. Cuts through the x-axis like a line. Here it's swerving through the x-axis, and that is the distinctive shape of a cubic equation. So if I zoom in here again on just this, the swerve that we're saying is that it's coming up, and then it flattens out, and then it curves up again, kind of like a swerve would be. You're going to straighten out here and then swerve back up. And so that's distinctive of a third degree or a multiplicity of 3 at that particular root here, right? That indicates that exponent. So going back to what I was saying about repeating as a factor, remember that this equation here, so let's eliminate this part here. When we look at this factored form, if I rewrote this equation exactly the same way, except instead of saying x minus 2 squared next, I say what that really means. That means x minus 2 times x minus 2. It's going to do the same thing at that root. And then finally, instead of x minus 7 cubed, x minus 7 times x minus 7 times x minus 7 times itself 3 times. There we go. And you can see I get the exact same image that's in blue and in red as what's in green, right? Those two things are overlapping each other. So no matter which color, standard form, factored form, whether it's condensed like this or expanded like this, they're all creating the exact same line. Now, the next thing that we want to talk about here, hopefully that gives us a little better understanding of the roots and multiplicities of a polynomial, is what we call the end behavior. So specifically looking at the standard form here, we're going to want to look at that biggest exponent, x to the 6th power, and see that it's positive. And what we want to notice about that is that on these positive even, 6 is even, exponents, the end behavior works such that it's going up, it's going in the same direction here on both of these ends, right? Here's the middle where all of the action is, where all of the turns are, and then out here on the ends, it's going in the same direction. And we would say both of those are going up. So let's think about this left side first. Remember that when we talk about end behavior, we say first that the function, right, so f of x goes to, that's what this arrow means, a specific value. And if the graph just points up like this, then we're going to say that it's going up to positive infinity. It's never going to stop going up. And then we say as x goes in a certain direction. And what we want to get about this graph is that this graph is going up, the function is going up as the graph traces itself to the left. And the left here is going to be continuing to go to the left is going to be negative infinity, whereas continuing to go up is going to mean positive infinity. So here we would say as x goes to negative infinity. And now we're going to say on the other end, so let's use a different color here. Over here on this end, right, that's why we call it end behavior, because we're talking about what happens at the end of the graph. We're going to say a pretty similar thing. This graph, though, is going to the right and up. And it's continuing to do that. So that up will mean positive infinity, and that right will also mean positive infinity. And then we'll say very similarly, the y values, the f of x, the function, goes up to positive infinity as x goes to positive infinity. And what we want to understand about this particular part here is that these are the only two missing blanks as far as all functions are going to go. When we talk about end behavior, we could basically copy and paste what we see here, this part, at the start of any problem. Because we're always going to have the x values go to the left and always going to have the x values go to the right. Those are independent variables, meaning they're allowed to go that way. But the dependent part, the y part, the up and down part, or potentially it leveling off to a certain value, what we would call an asymptote, right? That is what we need to be careful about. So if you have to answer an end behavior problem, you can basically just start off with this structure and then fill in what we need to fill in as far as does it go up when it's going left or does it go down? And does it go up as we go to the right or does it go down? So these parts here and here, all right? Okay, now one last thing here about polynomials that we want to make sure we understand. We understand the multiplicity and the factors, and hopefully we understand the end behavior a little bit, is that these functions are really easy to spot as even or odd functions. And that all comes down to the biggest exponent again. So we already should have known some information about this being x to the sixth power in either format, because the fundamental theorem of algebra tells us that the number of roots, right, complex or real, that we are going to have with any polynomial is going to be indicated by whatever that biggest exponent is. So looking at the standard form and seeing x to the sixth, that automatically means that there are 6 of these roots here. But what we're only seeing are 3. That does not mean the other 3 are imaginary or complex. Like we see here with the multiplicity, if we add up those exponents, x to the first, so 1, plus 2, plus 3 is 6, giving us the exact same highest order exponent that we have in the standard form. So understanding all of these things together is going to make giving us a better visual picture of any polynomial that we have before we even get to see the graph. And as you're trying to learn to analyze and understand these, I highly recommend that every problem you have to deal with, you graph almost instantly, just to get that visual picture. And then you start picking apart the pieces that you see in the picture and trying to understand them with the numbers in the equation. So a lot of the things that you see in this equation, like for instance, these coefficients, are not going to be showing up on this graph at all. But one of the things that you will always see that shows up is this constant term. Remember that the constant term of a polynomial is always going to tell you that y-intercept. So when you look at this particular graph, we would have already known that this crossed that y-axis here at negative 4,116, because if we plug in 0 for all of these x's, using that zero product property, 0 times all these values is 0. All those zeros added together are 0. So it basically says 0 plus negative 4,116, giving us that immediate response. So one of the things you want to make sure you're studying is end behavior of polynomials, the roots of polynomials and their multiplicities, and understanding any other key features that you might need to. That's it for this video. Hopefully that